Final session. Next talk is being presented by Carol Stoker, together with co-authors Jennifer Heldman and Elder Noda Brea, and it's mid-latitude ice-rich ground on Mars, an important target for science and in-situ resource utilization on human missions.
Okay, so much like some of one of the other speakers, Jim Rice, I think it was, I'm going to kind of modify my talk in real time here because there's sort of an elephant in the room or microbe in the room that isn't being talked about. So I'm going to talk about that. What prompted this submission was a paper that I'm a co-author on, Jen Heldman, published in Astrobiology in 2013, which basically looked at the Arcadia Planitia region and the locations where Byrne et al. Had discovered craters that revealed fresh ice.
Would you mind pointing out Arcadia Planitia?
Sort of over here. Sort of a big block of over here.
Okay. Thank you.
45 degrees and 45 to 50 degrees and 160 to 190. So in this paper, Jen and her colleagues looked at each one of these fresh crater sites and looked for a suitable landing site for human exploration over a 25-kilometer landing width. Sorry? Unmute. I'm mute, okay. Well, so, yes. I talk pretty loud, so I wouldn't notice. Okay, so basically, looking at each of these sites, she picked what was the mattress site. So this is actually the site that has the least of anything in it. So there's no rocks, there's no features of any kind. It's except that it is covered by these 10-kilometer scale polygons, and that is what the ground looks like in this entire regional area. It's covered with polygonal ground. Roughly 10-meter scales, yeah. So,
You said 10 kilometers.
I'm sorry, 10 meters. I'm getting flapped here by the microphone situation. So anyway, I have actually gone and done the exercise, but I think that we're all tired of looking at little green dots, and so what I'm going to talk about instead is what the implications of exploring this regional area might be. Other people have talked about all the nice geology that might be there. I liked Donna's site better than the things I was able to pull up in this, what is Jen's favorite site for landing. Jeff, in the previous session, mentioned this paper, which is showing that there are tens of kilometers of ice. Sorry, tens of meters. Kilometers and meters, screwed up again. Tens of meters of ice throughout this entire regional area, and that it's inferred to be up to 75% ice in places. So, and this is based on the Charad radar data and also calibrating it by looking at terraces in a terraced crater. So, mid and high latitude ground ice is an important target in the search for modern life. This search likely doesn't require any travel beyond the landing zone. And the reason is that climate modeling studies show that liquid water can occur where the ice is near the surface as orbital parameters change cyclically. So this is basically what happens. In the northern plains, it's low elevation, and the pressure is always above the triple point of water. So liquid water is stable. So if it's warm enough, the ice-rich soils in the near subsurface are a potential abode for life. Now, Mars obliquity varies, as we have a great talk by Jim Head at lunchtime about this. So right now, obliquity is low, and it's very cold. So any life there is in a frozen state. But over time, the obliquity of Mars changes and the ground warms up. And when it's warm enough, it can melt. So this is a plot of obliquity over the last 10 million years. As you can see, as you go back below about, or beyond about 5 million years ago, the obliquity was quite high. And it actually cycles up and down. And that cycling up and down occurs at a 125,000 year interval. So when the obliquity is above 33 degrees, the ground ice at the subsolar point, and I'll talk about that a little more later, can thaw up to 35 centimeters deep. All the way up at the Phoenix landing site at nearly 70 degrees north, at 45 degree obliquity, the ground ice can be as warm as minus 20 centigrade down to 75 centimeters. So that is actually the limit for microbial metabolism. It's not 0, it is minus 20 centigrade. So essentially, by drilling into the ground ice a meter, you can explore the history of ground ice over many cycles of obliquity and the potential for growing microbes when things are warm. Okay, so I was the head of the Biological Potential Science Working Group on the Phoenix mission, and published this paper, The Habitability of the Phoenix Landing Site, which asserted that Phoenix found habitable conditions in the high latitude ice at the Phoenix site. There was evidence for liquid water in the form of segregated ice that potentially forms by freeze-thaw processes. There was 3 to 5% calcite in the soil, a mineral that only forms in the presence of liquid water. And there was this soluble salt, perchlorate, which was patchy, suggesting that water had moved it around. It's very, very water soluble. Furthermore, perchlorate is a biologically available energy source. And it is very high concentrations as revealed by the Phoenix instrumentation. 1% is actually a huge concentration, and it's virtually unknown on Earth at that concentration, except it used to be found in the Atacama Desert at that kind of concentration. The absolute surface of Mars is lethal to microbial life because of ultraviolet radiation. But it doesn't take much to shield you. And Phoenix found transparent or semi-transparent grains of soil, which also allow a bug, a microbe, or a microbial colony to live underneath even 1 grain of sand. There are benign environmental conditions, but currently it's too cold for growth. So because of this obliquity variation and the inference that it could actually be warm enough for growth, several of us have been involved in this Icebreaker life mission study that's been going on for a number of years now and has actually been proposed to the Discovery program this latest round, unfortunately without success. So the PI is Chris McKay. The spacecraft is essentially the Phoenix lander provided by Lockheed Martin. It's carrying a 1-meter drill built by Honeybee Robotics and 3 instruments. The signs of life detector, the laser desorption mass spectrometer, and a wet chemistry laboratory supported by a set of cameras from Malin Space Sciences. So here's the science objectives of this mission. Biomarkers basically search for biomolecular evidence of life. This really means biomarkers that are commonly found in terrestrial organisms and are deeply rooted in the tree of life. A positive detection indicates a life form that shares biochemical traits with Earth life. And this is addressed by this instrument, the Signs of Life Detector, which I will talk about more in a minute. Second objective being, is there just general organics at this site? So biomarkers without a lot of other organics would be very suspicious for potential false positive. So there's a second instrument, which is the laser desorption mass spectrometer. So the whole idea of this instrument is to search for organics with a method that is not confused by the presence of perchlorate. Because perchlorate reacts with organics when the organics and the perchlorate are heated up together, perchlorate has essentially fooled 3 different missions that have gone to search for organics. And it's finally the SAM instrument that has managed to tease out presence of organics on Mars after many years of work, actually, on the part of a postdoc. So the other instrument would be a habitability potential instrument. This is the wet chemistry laboratory. And I must be going way too slow here. So, okay, so the signs of life detector. This is, think of this as a immune system in a box. Basically, what this does is it simultaneously searches for up to 150 separate biomolecules in 3 classes, which include things that we selected were information, metabolism, and cell structure, using a technique called fluorescent sandwich immunoassay. The instrument has been widely tested in Mars analog environments. We're taking it to the Atacama this coming February to do more testing in the most sparse, biologically sparse soil on Earth. And then in addition to this, we have laser desorption mass spectrometer. Again, the idea of this is that you shine a laser on the sample, it directly drives off volatiles, and they are directly detected by a mass spec, so there's no heating involved, there's no reaction with perchlorate involved. It's been shown that in samples mixed with perchlorate, you still see a signal. So, and then finally, the wet chemistry laboratory will be a direct copy of the instrument flown on Phoenix, which originally detected perchlorate. So, a 1 meter drill. As I mentioned, the ability to just go down a meter and sample and provide samples to your instruments allows you to characterize the past history of habitability over many cycles of obliquity. So basically, we've got a drill system built by Honeybee Robotics. It's a 1 meter drill. It augers cuttings from dry soil and ice-cemented soil up to the surface, which is then brushed off the drill into a scoop, and then the scoop deposits those samples into the instruments. The drilling system has been field tested numerous times. It's gone to the Antarctic, it's gone to the Arctic. We just recently took it to Rio Tinto, Spain. Okay, so the mid-latitude ice-cemented soil, or icy sites, have rather interesting and different conditions than would be true for the very high latitude site where Icebreaker was sort of designed for, which is the Phoenix landing site. And that is the fact that the phase of perihelion is important for the amount of insulation that the site experiences. And the next slide, I think, shows that. So this is from a paper, Richardson and Mission in 2005, which is looking at the presence of liquid water or potential for liquid water in terms of pressure and temperature conditions. And this is what you get in the current epoch. And I realize it'd be hard to see, but these blue areas represent the light blue color here is 100 days a year that temperatures are above freezing, and this is the number of hours per day. So, okay, so, so this is at the current obliquity and current phase of perihelion, and this is 25,000 years ago in northern summer. And what you can see is that it's actually in this mid-latitude region. There are lots of days that temperatures are above freezing. And presumably, melting will be occurring into the subsurface. And this is what happens at high obliquity, 45-degree obliquity. And what happens is this entire sort of region moves north. And it actually isn't better here in the mid-latitudes at high obliquity than it is just at the opposite phase of perihelion. And that is happening at a 50,000 year time scale. So just one more thing about perchlorate. Perchlorate is a strong antifreeze. It drives the freezing point at its eutectic down to minus 70 degrees. It is a chemoautotrophic nutrient. You can live on perchlorate if you are the right kind of microbe. But it's toxic to humans at parts per million concentration, which is a lot less than is on Mars. So don't grow potatoes in Martian soil. Okay, so nearly 40 years, this is the cover of Astrobiology in July. Nearly 40 years after Viking, are we ready for a new life detection mission? Was the question asked on the cover. And yes. Okay, so I did in fact draw little lines on the charts and have little green boxes and all that, but I think the data needs for these sites are that we really need a more to look at the climate models for this mid-latitude region. We've looked at them for the polar regions, and really need to further understand the astrobiological potential of the ground ice in the subsurface. How warm does it get subsurface? Is anybody is a modeler and wants to do that? Come and talk to me. I really think that a robotic search for modern life should be accomplished prior to sending human crews to Mars, whether you send them to the icy deposits or not. Icebreaker is technically ready to search for modern life on Mars and can be accomplished for a modest cost. A discovery-like cost. That's it. You're still scary.
Which one?
Your clicker's right there.
Okay. It's clear to many who know me that I am not qualified to talk about biology or geology, even how hard Carol, Penny, Chris McKay, Victor Goston has tried to teach me over the last 15 years. I've learned a lot, but not enough to be among your illustrious level of knowledge. So I'm not going to tell you your business as geologist, but I am going to tell you my business. And I'm an historian, also a public relations and a lobbyist professional. So I do know about PR and about writing history, and not just about writing about history. And I think what we might forget in trying to find the most hip location for our research is that the world will be watching. That first step on Mars will be a pivotal moment in our human history. We've had other pivotal moments, but I think at the moment, at this, 20 years, 18 years before we put that first foot on Mars, we are at a very unique moment, a unique opportunity to know beforehand that we will going to write history. And perhaps we should take that into consideration. And if I say writing history, you probably think, this will be happening in 2033 or 35. Yes, probably. But what you kind of not take into account is the fact that the grandchildren of our grandchildren will be talking about this moment, that this will be written into the history books, not just, the next 20 years or 50 years or few centuries, but probably in the next many millennia. And knowing that, I think we need to try to get it right. Now, this headline was getting it half right. It understood it was a pivotal moment, so it got a call sign for the lander, the Eagle. I'm pretty sure if it had been a Chinese lander, it would have been called the Dragon. If it had been Russian, it would have been called the Bear. So it was American, so it was an Eagle. But what they didn't get right is where they landed. So, like I said, we chose Copernicus crater for the reason that it is honoring Copernicus, a man who gave us a very different side of who we are. Now, this is Copernicus crater, and if I'm going to go ahead with pushing for this side, I will request a lot of high wish images, because Copernicus crater apparently doesn't have too much. It has some measurements. Like I said, I'm not qualified to talk about olivine dunes. I know they are interesting to you geologists. There are gullies, there are craters with gullies within Copernicus. Oh, Copernicus, yes. It's on the edge of where we can go here, 50 degrees south. So I'm not going to talk about the gullies, although, they are important. There is ice there, there is water there. I'm not even going to talk about how in earlier times the water was draining into Maadim valleys, into Gusev crater, and then further north. Like I said, here's where Copernicus is, and I've been so brazen as to center the molar map on the 180th the east degree instead of 0, because then, as you can tell, it kind of drops off the map. It also, because it then overlays with this map, because when we were starting to look into where would we put humans, we of Explore Mars actually were driven by the idea, if we send humans to Mars, we want them to thrive, to do their business, to stay as healthy as is humanly possible, and to get them back. And there was this idea that, if you send people where there is magnetism, remnants of magnetism in the ancient crust, because we're talking about 3,000 million years old crust here, then they would be safer. Now, as you can see, the highest elevation of nanoteslas is 666. That's right next to where... Oh, yes, I was supposed not to do that. Could someone help me? Thank you. Anyway, so here is the Copernicus crater. This is the most you can get of being protected against incoming cosmic rays. And if you then know that on Earth it's between 20,000 and 60,000 nanoteslas, you understand that this only helps a very little bit. So I'm afraid that's not going to help us. What's nice is that the round circle is about where Copernicus is. There's lots of water, which has been demonstrated, at least in the first meter. I'm always wondering, as a layperson, am I now looking at, the northern landscape of Scandinavia, the tundras, or am I standing on the top of a polar sea that has been frozen, solid with dust in the water? And we don't know, of course, because these measurements didn't look any further than 1 meter at that point. This is there are no proper nice images of this region. Thankfully, I know Kees Wenenbos, a Dutch space artist, and he was kind enough to use the molar data to get me this. And, Copernicus crater all the way down there. And this is, zooming in. This would be about the exploration zone. I've centered it there because there are some interesting gullies in both there. But like I said, there's not much information, especially for me as a layperson, on this crater. So that need to be looked into. We need lots more data. Like I said, we got it half right here. The Eagle has landed. What we didn't get right, Sea of Tranquility. What exactly was the message the United States of America was sending the humans of Earth? We need to be peaceful, tranquil. So, this is a huge moment. And if we scientists want the rest of the Earth to be interested in what we are doing and to foot the bill of this mission, I think we need to think in the PR wise, and that's why we ended in this crater, because Copernicus, with his book on the heavenly spheres and their how they were orbiting around the sun and not around the Earth, this changed the view of who we were. Up to that point, although there were some dissenting voices, everyone viewed humans as the center of the universe, because Earth was the center of the universe. Which they thought they were observing. This was what they thought it was. This is what it really is, we know now. But, it was Copernicus who mathematically proved this and published this in 1543, so quite some years ago. But seen in human history, or even in the history of science, 450 years ago, it's not really that long ago, and up to that point we had a very different view of who we were. He started a renaissance with his book, in science, and I think choosing Copernicus crater is telling the world that we understand this is a pivotal moment, this first step. We also say to the world, we understand that we are standing on the science of people before us, and honoring Copernicus. I've of course thought of others. Huygens would be out because only 30 million people on Earth can pronounce that properly. And why make the rest of the world feel inadequate when they don't? And there are some other names that I think would fall short of them being the right spot, because they're actually honoring persons that, and in this day and age, would be standing in front of the tribunal in The Hague for, crimes against humanity. So that wouldn't be a good choice either, PR-wise. So what I'm saying is, Copernicus crater, that of course is just a point in the landing site that I've proposed. Then, if you look at the Martian, Hollywood, Ares 1 is, so the god of war in Greek is sent to the god of war in Latin. Let's do it this way, because that's a very different message. And, if we want to argue, does the audience know why it's the Apollo project? Do you want to know? Okay, that's my field actually, because I have a master's degree in ancient history, and as my names are Artemis, Ariadne, you understand that I know a great deal about Greek mythology. So in Greek mythology, you have the son of the god, the sun god, which is actually the Titan Helios. And I hope people have read Percy Jackson, because then you know a bit about the Titans and the Olympians. And now Apollo is an Olympian god, and there was an advice in May 1960 by someone who actually didn't probably know his mythology too well, and this person wrote that, Apollo is the god who is leading the chariot of the sun. No. Oh well, close enough. And so the Olympian Apollo then was chosen to be the symbol of, us going to the moon, which I always think. So Apollo goes to his twin sister Artemis, who actually wasn't really this goddess of the sun either, because it was a Titan goddess, Selene. But later on, in the Roman era, that was, they were saying, Diane, Artemis is the goddess of the moon. So Apollo goes to his sister. Great, why not? And I propose Aphrodite goes to her lover, because Ares was her lover. Thanks to all these people for the images I used, and writing history, let's do it right this time. That's my opinion.
Do we have a talk from Hamilton?
Yes.
I've got to say it last but not least.
Yes, thank you.
Okay, is that good? All right, saving the best for last. Don't leave. Here. Okay. So anyway, this is our team. We did start with a diverse team of geologists, astronomers, ISRU people, and astrobiology. So we did look at this from a comprehensive viewpoint. We do have 2 sites. We probably should have put in 2 papers. I didn't know that was allowed. So you buy one, get one free. I'm going to talk real fast so we can get through both of them. And traditionally, aloha. All right, very good. Now I can start. All right. So instead of pointing on the map, here they are. They're diametrically opposed, one in the north, one in the south. They're very similar, but for different reasons. They both have a lot of water and a lot, I'm going to convince you, a lot of scientific interest and ISRU capability. A little bit closer up on it. So we're going to start with the southern one, Ausonia cavis, which is down here just above Mesopotamia. So I think that puts me in Iran or Persia, if we follow that analogy. No green dots, but lots of different areas. This one, it is very rich. It's at the very top of these valleys, but centered on a archaeolake. Here's the geologic context. Up to the up in this area here is a very large Noachian volcano and older terrain, all flowing downhill here, and then a Hesperian volcano up this way, so they converge in that area. We've got the a couple of theories about how these formed, and depending on which one you want to buy, it doesn't matter because both of them depend on a lot of water. So that's the point of that. And our science ROIs, the head of this valley outflow area, you can't really get down into there due to the slopes, but at the very parts where these areas are beginning, should have a lot of interesting areas. It's somewhat chaotic terrain there. You got a lot of faulted basalt, a lot of small channels, and the beginning parts of the drainage that goes down into the Halys Basin. And a lot of well-preserved craters. Be very good for some dating and strata. Number two is the main feature here, Ausonia cavis, which is this archaeolake. There's some fairly good data, a couple of high-rise and some chrism. But the southern part of it, the outflow area, is very easy terrain to get into. And it's the floor has got all these large areas that have been water is gouged around as it flowed out, and should be a lot of clays. The chrism data I'll show you in a little bit. The other part of here is the Hesperian shield volcano that's up to the east of it, no, west of it, sorry, which flows down. So it's good geology and a lot of basalts, a lot of good dating techniques. Down up just north of here is yet another lake that's still within the exploration zone, and there's it's a lot more difficult to get into. It doesn't really have a drainage site. However, it could have just all evaporated out. There is a large landslide on one side. So. And then down inside the, excuse me, to the north of this, there's this whole area has a lot of Noachian massives that are populating the entire area. And so this is one that's just right on the edge that could easily be gotten to for a rover or traverse. It's fairly flat land going up to there, so you can get to the base. And a lot of datable material there, possible fluvial structures. This shows basically the generalized slope over a much larger area up from the Noachian volcano and from the Hesperian volcano. So everything's flowing down to this area here. So with the astrobiological potential, we've got sediment deposits. We've got typically all the mineralogy you'd expect from an evaporating lake, and as well as some flow structures. And typically with the two volcanoes, you're going to have water-altered basalts as they came out. So a lot of different mineralogy should be rich in that. And for our resources, down into the southern outflow, the first, we've got some hydrated minerals, possible subsurface ice. It maybe have a lot of loose material. Into the floor itself, you can see some of the dunes that are around the sides. A little bit of dust, sand, and clay. So this material here, as well as some of the material on the outer part, would be very, very suitable for construction, ISRU on basalt sands, doing sintering, construction, as well as water extraction. Here's the chrism image of the interior of the floor, and showing some iron and magnesium phyllosilicate features, as well as on the walls of the lake there, there's possible RSLs, and it does look a bit dark at the bottom where things could pool. So in that slope. And then the other thing is the very head of the valley outflow, not going into here, but this little area here. It's just got a tremendous amount of structure and erosion. A lot of sediments, and just to remind you, everything was flowing downward into here, down into the basin. And then of course, you got tourism, right? Can't forget about that. I have no idea where this came from. I found it on the web. So somebody's been there way before us. Okay. So little green dots. This is fiction. We filled it out the best we could, but at least we filled it out. That was the hardest part of the presentation. Okay, so I should be halfway through, I hope. Yeah, so good. Yeah, all right. So now we're on to the other. This is up in the north area, and this is the headwaters of this flow channel that goes out to the northern sea area, and it's got some rather interesting techniques on its own. The landing site we've chosen is at a flat area around here, which allows you to move in and into the flow. You can get up to these areas here, as well as come around here. And the nice thing about this geologically is that all of this area over by the photographer is flowing down into that area. So you're going to be sampling a lot of the geology from a very large terrain. Here's the geologic context. It does have some older areas, a lot of some Neogian and a lot of Hesperian, and going through on the science ones. This is the entrance and slope going down into the flow channel, so it's accessible. It's going to have a lot of fine materials. Here shows basically the drainage from this large area of Mars, and everything's just pulling down that way. So we're going to have a lot of sedimentary material pulled through there. We've got the first major curve in the flow channel. It's very wide, so we're going to have our typical gully features, and as well as erosional on the outside and the inside of the bend. So we'll have sediment sorting and larger materials on one side, fines on the other. And this is there are also multiple inner channels, very small ones, showing there's been multiple flows over this period. This channel has lasted for a while, and sort of say that because right at the very beginning of the channel is this buried crater. And since this is a lower area, this impact probably occurred after the channel was first formed, and then later there was flows later that filled it in. So this crater can definitely help date the areas of this flow. Going down to the beginning of the beginning of this, you've got a lot of this really etched out terrain, a lot of the butte-like structures, and this is all feeds in up to the north. And for the astrobiological aspect, that we've got a lot of flood events in here, and it's moving sediment around. You have great potential for forming fossils and biosignatures in the rocks, as well as perhaps some groundwater reservoirs that may still be there. Okay. Right, so where this is, okay, we forgot to put latitude and longitude. Anyway, this is the outflow up here. Oh, let me go back. This is a rather interesting one. So this is the flow channel. This crater here, there's a high-rise image of it, which just barely nicks the edge of that. And on the edge of that is a little tiny crater, which this wall here has collapsed, and you definitely have a fluvial flow out there, maybe a glacier. We found that very intriguing, and that just could be solid ice sitting there under a little bit of regolith. As to how and why that broke off, did the crater fill up and the wall collapse, or was it a heat flow? That's for layers to fall out. The other resource is this buried crater right in the flow. So we've got a lot of depositional material, fine grains, very suitable for feedstock for ISRU, and water alterated minerals there. Then these are just discussing the inside and the outside of that first curve on the flow, so we can pick up water resources there. If there isn't significant ice reachable, we could process it out of the material, as well as having sands that are basically wet, and we just extract the water out of there. Okay. And then lastly, this is sort of an overview between day and night thermal properties, showing that the big incident of on this outer part of the flow channel, the very bright signatures there with the dust, but not too much down in this lower area. Okay, so then of course our green dot diagram as best we could, and ROIs. I won't go through these. You can read these later when they're posted. And then the needs for both sites is basically the southern one has a couple of CRISM data points. The northern one we could not find any on there. There may be, but maybe we didn't look hard enough. But that would be very useful for that. And then of course more high-rise imagery, and then definitely ground penetrating radar to see what's on the subsurface. So that is about it. Gosh, I went through 2 in less than 15. Woohoo! Okay, so.
Could the other two speakers come back, please? Oh, they're so close.
There we go. We kept you on time.
Okay. That one's working. Here you go. I mean, if we can get a couple between us.
Here.
Oh. Okay. Any? Yep. Any questions? For any of the presenters? Thank you.
So I guess a comment for Artemis. First of all, thank you very much for your perspective. That's not something we hear very much in a meeting like this. It's good to think about those things. But I want to suggest an alternative to choosing a landing site based on an appropriate name. There's a dirty trick that you can use that the Japanese did with their first asteroid mission, which is this asteroid had some technical name that no one had ever, just a bunch of letters and numbers. When they got there, they renamed it. So if you have the right name ready and just say Copernicus landing at, Jezero Crater, to pick an example from yesterday, you might be able to do that. And so have your technical cake and eat your PR cake as well.
You have no idea how history books will vilify you for something like that. Because the rest of humanity isn't stupid.
Well, I didn't see anybody vilifying the Japanese for renaming that asteroid.
Yep. In the middle. The furthest possible distance from a mic.
Well done.
Yeah. Okay, here you go.
2 for 2. Thank you.
Okay, just a quick thing, because I want to make sure that this audience hears it, about the perchlorate. So Carol, this is something that I've actually learned since Phoenix, is that perchlorate is not terribly toxic to humans. It was actually used as for decades pharmaceutically to combat hyperthyroidism, and in some instances is still prescribed today. So low doses of perchlorate over a long period of time are totally fine for humans, and the way to get over it is just to take iodine tablets. So I just want to make sure that was just a really minor point, but want to make sure that everybody's kind of on board with I'd love to pass you the paper that I found. A guy just 5 or 10 years ago wrote this big review, had nothing at all to do with Mars, about perchlorate as the use of perchlorate in humans, and it's something that has kind of been studied for years on the side by the medical community because it was actually used to treat disease. Kind of interesting.
I just want to add a quick caveat to that, and that you're right for adult humans, but if you're talking about child development, it is still detrimental to child development if they're exposed to perchlorate. So,
well, it can't. So this is we can talk about this later. But it's interesting. This is
just
kind of
be
a
careful
story.
about that.
But they showed with tadpoles that whatever the negative effects are can be reversed. But we're not tadpoles,
Right.
and at least unless we get reverse aging on the way to Mars, I don't think we're
but
sending children there yet.
If you're talking long term, who knows?
We're also, I don't think we're used to 1% kind of concentrations. I mean, my understanding is that it's considered a biological hazard remediation zone if it's a part per million perchlorate in groundwater.
If you're eating it all the time, like so, the bottom line is don't eat the dirt every day.
Well, if you're eating plants that are grown in the dirt, I'm just saying, I think this needs a lot of looking at, and I appreciate that there has been some medical work done.
Or at least make sure it's clean dirt. Lauren Markle, question for you, Carol, on the search for life. We talked about perchlorates and how that is not compatible, or possibly not compatible, but in Earth, we have seen life in the most inhospitable places all over the place, very nasty environments. It seems that we are looking for life, Earth-like life, because that is what we know. Are we prepared, and are we looking for life that has something that we don't even realize might be there? And how do we detect that?
So that, in my view, that probably is only doable by humans on the surface. I think that, so the Icebreaker mission actually plans to look for Earth-like life, and actually under the hypothesis that Earth and Mars have shared material during late heavy bombardment when life started on Earth, and that there probably is a common ancestor if there is a remnant of life on Mars. If there is organic life, but is not anything at all, like there is an independent origin of life on Mars, and it's nothing at all like terrestrial life, so you can't look for it with the immunoassay technique, then the immunoassay would see nothing, but the organic assay would see probably significant signal. So there is some way to discriminate. But probably the thing that is of most risk for Earth-like life is for us, is Earth-like life. So, you can always hypothesize a mode of life that's nothing at all like us. It's based on silicon or something. But, yeah, we don't know how to look for that.
I can answer. David Wilson from NASA Ames. There has been a lot of studies on perchlorate in more recent times, and it shuts down the thyroid gland, but it doesn't hurt animals, and it's accumulative, and that's the real issue. So long-term exposure to it can build up, can result in your thyroid gland being not operating as well as it can be. And the issue is, it's about management, and there are plenty of people around on mine sites and in processing plants who've lived and worked in very heavy metal environments and dangerous chemicals, who, as long as they manage dust and have regular blood samples, they're able to track and deal with contaminants like perchlorate.
So I wanted to just clarify one point, which I think you may have misunderstood from my talk. Perchlorate is a resource for microorganisms. So it actually is for chemoautotrophic organisms, which are the organisms that would live under the ground in the ground ice, if in fact there is something there. That would be a way that they would get energy instead of from sunlight. So the chemoautotrophic organisms can metabolize perchlorate, and it's actually very similar to essentially oxidative metabolism. So because there are so many oxygens attached to a perchlorate molecule that those provide a huge amount of chemical energy. So it's very energy efficient. So there are lots and lots of organisms that take advantage of this.
Brian
Honor.
Day with Survey and S. Ames. John, do you have any indicators of what kind of a road cut Casey Vallis makes within your EZ, and if so, the nature of the strata that it exposes?
I'll let Colin answer that.
Yeah, I'm the geology member of the team for that.
All right, Colin.
And so for Casey Valles, it's a very deep cut and a well-exposed strat section. It goes down to the Nochian level, and the floor of the channel is dug into the Nochian sediment.
Very good, thank you.
I have two questions. One is for the John, and the other one is for Carol. John, where is the best place for the analog for Mars? And that is for you and the Carol. How much do you expect to have the international collaboration for the Mars with mankind?
Well, okay. Well, of course, the answer to your question is Hawaii. We've got basalt all over. We can operate every day of the year, and it doesn't cost millions of dollars to go there, like some of the colder areas. So, and the geochemistry is identical to Mars, proven. So, well, everyone's welcome to come to Hawaii to test analogs.
According to his request, my question.
So I guess my answer to what is the potential for international collaboration on manned exploration of Mars, human exploration of Mars, I would say the answer to that is way above my pay grade.
What's your answer, Steve?
Actually, I hope that the audience is aware that Explore Mars is very much in favor of this international cooperation. It's one of the reasons, I think, that I, as a non-American, are president of this organization and part of the board of directors. It makes for easy access to other parts of the world. For ESTEC, of course, I live in the Netherlands. That's not too far from me. And, in France, Paris is only 4 hours drive. But also because I have a Dutch passport, if there needs to be talk to the Chinese or to the Russians, I can go there. My government actually encourages trade and all kinds of cooperation with a lot of people. Russia is a bit iffy because they downed a airplane last year with 200 Dutch people aboard and 100 other nationals. But the 200 Dutch, of course, grated on our national feeling of safety. And so that's a bit of a problem at the moment, but it's not a real impediment. So yes, we are trying to get to further the word, to do our H2M conference in ESTEC either next year or the year after that. ESTEC has invited us to do it there. And so, yeah, we would very much like to cooperate like the ISS, because, it helps a lot if you cooperate. Perhaps it doesn't really speed things up, but it does help.
Stan, you got a comment on that?
So the decision on international collaboration on humans to Mars is made well above my pay grade as well. But I know what they're telling us as we make our plans, and that is it will absolutely be international. There is no way the U.S. can afford to do this alone. So everybody's invited, but the ticket price will be high.
How high?
I have a question for Artemis, actually, PR question. So we had a couple comments today about astrobiology and how the public wants to know if there's life on Mars, and I think everyone here wants to know that too. So it's easy to sell that. But when we talk about Graben and craters and impact processes and rock types and things like that, it's a little bit more difficult to explain to the public how important that is, because I think it's important to everyone here, but it's difficult to communicate that to the general public. And so in your experience, have you learned anything, or do you have any nuggets of wisdom to pass on to those of us in the room to better communicate why what we do is important?
If it was, let's say it's a product we're selling, then the product needs to get the job done for the consumer, so the people we are, addressing. So we have to find, what interests them in their lives, in their neighborhood. So for parents, very often it will be like, the education of my children. Grandparents the same. So if we can hook into that, of course we're trying that with STEAM and STEM. Next to that, if I went to Iceland on a geological expedition, and I met a lot of people there, and only there did I learn that lots of the extremophiles are being researched by pharmaceutical companies, because actually they hope, that from these critters they will find cures for whatever is ailing us. And going to Mars, we might find a cure for baldness. That would speed up, getting us there, I would think. No, I'm looking at no one in particular. And so, so basically it is, what you have to sell to the general public, that going to Mars is, is a big, it's part of who we are, exploring as a human race. But also, that's too high up, for most of them. But, telling them that, what we learn there helps us to manage Earth, to manage, if we go to Mars, we will have to wazoo about recycling, right? We have to really the shit out of science here. Well, in that case, to talk Mark Watney's vernacular here. So if you go to Mars, you have to recycle, you do a lot of things that are actually important for us. Water management here on Earth, which will help their local community do it better. So there are a lot of things that we will learn to do, or we have to learn to do, which will immediately be applicable to here on Earth. And those are down-to-earth, normal day-to-day things they need to do. So that's what we need to sell. And then, you're the scientist, you can tell me, whether this, looking in this crater will help whatever I'm doing day-to-day in life. That's what you need to look. If you can find that, you can sell your crater. No problem.
One more? Yes. Say who you are.
Hi, Laura Kerber, JPL. I wanted to add to that and to say, I think that there's these two huge groups of the public, and it's kind of a Venn diagram, so they overlap. But there's the people that are very excited about astrobiology and finding life in the solar system. And then there's another group that wants to live out there in the solar system and would love the idea of living on another planet or traveling there or something like that. And so they're the explorers. And so some of those people aren't interested in whether or not there's life out there, and some of them are. And so some of them interact and some don't. So I think both of those groups of people are people that we can really appeal to in one fell swoop with this project.
I have one more comment. If we're talking about, we use some hashtags. My own organization has been using Boots on Mars, which we very recently changed, because I think that's a bad vernacular. It's the vernacular of war. Are we going to send troops to Mars? No. Our hope is that we're going to send humans there to stay. We don't know, of course, for certain that we can live there, but, perchlorides and all the other problems. But so we don't know that. But, so it's imperative, if you talk about your field, that you try to find words that will appeal to the public. And Boots on Mars, I think I just heard 3.5 billion people leave, most of the females. And, Boots on Mars might even be an American vernacular, which means I heard 6.5 billion people leave. And the international corporation just went down the drain. So, and it's, you will say, what's in a word? Well, actually, language is very powerful. So choosing the right words for your project, for your geology, for your astrobiology, might actually help you to get the funding and so be able to do your research. It's as simple as that. It sounds, trivial, but in the long run it isn't trivial, and that's why big companies have these big departments that they use a lot of money of the big company to figure out what words will sell and will appeal. My humans on Mars, foot on Mars. I mean, we said foot on the moon. High heels on Mars, that's fine. Have you tried high heels? on a lava field? Not fun. So yeah, foot on Mars. So make it as normal as is possible, so it appeals to the common person.
Okay, there's a question at the back.
It's just another comment. If we went and talked to a general person on the street and asked them which of these three things they actually recognize and understand what it is, Neil Armstrong, Copernicus, or WD-40, they'll pick WD-40, which simply stands for Water Displacement 40. While language is important to being able to reach out to people, focusing on the hashtag for the exploration gets us no closer. The hearts and minds, we're talking about less than 1% of the federal budget going to NASA. We have a hard time getting enough funding to do what we need to do right now in the agency. So I think the best thing we can do is focus our efforts at this workshop and in the upcoming AO, so we have a front and a framework so we can show we're making actual progress and not quibbling about what to say about this on Twitter.
Okay, we'll have 5 more minutes, and then, so we've got time for probably these 2 more. Alex in the middle, and second row.
Alex Longo, the Cardinal Gibbons High School. I'm an ordinary guy who comes from an ordinary town, and and I certainly don't come from an ordinary school. The people at my school are amazing, but what I found is that space exploration is actually very popular among the Mars generation. Trust me, when the Martian movie came out, the next Monday, that was the only thing people were talking about. In my Spanish class, people are still talking about the Earth Science class where they were talking about space exploration. Everyone is just super interested in space and exploration and finding life in the universe and all of the things we're trying to do. So I think that reaching out to the public and getting the public to be excited about our mission is going to be the least of our problems. It shouldn't be something we're worried about.
Hi, I'm just going to comment on that because I think I'm just one generation up from you, so I can say a couple things too. And I think that's true, especially if you're surrounded by probably the types of people that you're surrounded by. But, you know, I've lived in a lot of different places, California, Las Vegas, and now I live in Hawaii, and my parents live in Seattle. And it really depends on where you are to be able to say that, because there are places, like in Hawaii, we have native people that I mean, there are people, I live on the Big Island in Hilo, it's a small town, and even though they have astronomers on a mountain, they, I can't say that they would be all that super excited about going to Mars. It's also a cultural thing, you know what I mean? So it is, I think we should worry, we shouldn't say, oh, it's no big deal, we shouldn't worry about it. That's kind of neglecting it a little bit. And if you really think about why NASA has such little funding, I think part of it is because we haven't exactly convinced the public that what we're doing is important.
I'm not saying I'm just saying that the public's excited about it.
Well, you said it was the least of our problems. I actually think it's one of the biggest of our problems. Without public support, we can't do any of the things that we want to do as scientists.
But actually, the public is supporting you. We did a national survey, we being Explore Mars, because we actually wanted to know whether we were these silly geeks being very much in favor of going to Mars, but being like, you know, in the 1 percentile of the population of just America. So we set out a national survey, which was done by a bureau, not by us, you know, the way a Gallup poll or something is done. And in February 2013, and we got back that 74% of the American population, and that was a national well-done survey, it wasn't biased or anything, 51% of the people responding were females, 49% were males, so, you know, and it was also all over, you know, the ethnicity of America, all over America as a country. So 74% believe that in 20 years' time, so in 2033, people would be walking on Mars. Then, you know, there is a problem that most of the public think that NASA has about 10% of your federal budget. And people worry about the 10%, you know, you understand that. So what we did in our survey is give the people, the next question was, you know, how much is the budget of NASA on the federal budget? And people were able to say between 0 and 6%. The average was 2.47%. And it is 0.43%. So the next, it's great, this age of electronic surveys, because the next page could say, it's less than 0.5%. And then we started to ask questions. So in a way, by telling them it was only 0.5%, we gave them this reference, but also we gave them comfort. Because now apparently, giving money to NASA wasn't going to impede the schooling of their kids or their social security or their Medicare or whatever. So because it's a very tiny bit. And then we asked them, what do you want us to do? Go to an asteroid, go back to the moon. They actually chose Mars, and that was before the Martian. So, but it was after Curiosity's landing. So, and after, of course, many years of Spirit and Opportunity. And then we asked them also, what's the reason we would go do this exploration of the universe? And this is something we brought to Congress. This is a very thick 60-page scientific report, because do you know what they chose? Why they want us to do space? It's cool. No, they actually, one of the choices they could make, because America is a great country or whatever, no, they chose science. They want to know stuff. This is the answer of your general public. So all we need to do is, feed them the right information, tell them we're interested, in what they think in it or something. I think there is a connection. There is a chance, an opportunity. And the whole science community, and especially the Mars exploration community, should grab that chance.
Thank you. One last one.
Yeah, and just more of a comment kind of to what you're saying there. The Martian was probably one of the best advertising things done for this effort. But that then really comes back to the question why we are going, because we're not going just for science. Yes, there is a lot of science there. There's a lot to learn about solar system and all of that. The general public doesn't know Hesperian from a hole in the ground. So, really when it comes down to it, there's a little video clip called The Wanderers. I think many of you probably know about that. That is less about science and about the passion of who we are as explorers, as pushing the envelope, about going beyond what we're capable of or what we think we are capable of. And to me, that is a lot of what this is about. And I want to make sure we don't lose that. Yes, the science is great. The science is fantastic, because that brings us a lot more knowledge to take that next step.
Right, well, I'm going to finish. The fact the last words were "science is fantastic" was an excellent way to finish the workshop. Well, with this portion of it. So we have a good break now. If you'd like to take a break for about 20 minutes, come back in at 5:25 for those talks from Jim Green and Jim Watson. That would be great. Remember, there's the rover outside if you want to go look at that. That would be great. And see you in about 20 minutes.